we have Haskell, inch, and metric. And you can switch between them anytime you want. Now, there's a lot of interesting things you can do here. When we interview users, we found that a great percentage of them are doing non-standard tools, or they'll mix and match. So they'll use some standard tools and a lot of non-standard tools. So how do we come up with a ability to deal with both of those? Notice the buttons of standard and non-standard up here. What they basically let you do is take a standard configuration, and then by making it non-standard, it turns off the catalog and opens up the width and length so you can size it to whatever you want. So if it's within a smaller range, close to a standard catalog, but you can vary the dimensions that way. Also, each of these things you see here are what's called configurations. It's like a part of the catalog. You can build your own configuration. So when you hit the pull down, you can see your shop's name and its particular configuration there. So if you're doing some non-standard tools, you can model this. Even if it's something really huge, or like a fascia or an instrument panel, model up the overall plate sizes, model up the guide bushings and the guide pins, and then save them. And the way that you see me going through this standard configuration, it will be exactly the same for your particular type of mold. So it's very flexible. Something nice about the system, too, is what we call bound data. Perhaps you noticed that gray box that surrounded the part. This allows you to work with margins. You're describing how much steel you want behind your kits, or how much steel you want around the inserts. So if you're doing direct cut plates, you probably won't need any behind it, but you'll set your margins to 0, and then it'll size the top of your direct plates. It could be that your mold base is going to be maybe nothing more than an ejector box and some components. Say that type of configuration, and then it will size the A and the B plate that you're putting into it if you're doing direct cutting on a non-standard tool. With this, you also can set clearances, and this is describing the preload condition on your inlet, a gap between those retainer plates. Notice when I set my margins, it has sized up in gray what those margins are. I'll flip off here real quick so you can see that. Okay. What it has also done is gone into the configuration and picked the most appropriate size. In this case, it's the largest one. So it does do some assistance in helping you find your mold base. We'll take what the system has given us, and we'll move on to the next panel, which is talking about plate thickness. And here again, be thinking about your process and what you're doing, and think of these pull downs reflecting the type of mold that you would be building. Here we can see the plate thicknesses. From here, the pull downs reflect what is standard inside this configuration. Here you can see up 2 7/8 sizes itself down. Looking at the ejector housing, you can pick a standard size, or you can type in whatever value you want. So by picking a non-standard size, my ejector housing is going to be reflected as a non-standard component in my bill of materials. By picking a standard size, now I'm back to, again, a standard type of component. So that will have to present on the bill of materials. Next, we're looking at the components. You can turn any of these on or off. Perhaps the sprue bushing, the lobe turn off if you're going to set them in somewhere off-center. In this case, let's just go ahead and build up all these different components. Again, those can vary to the type of configuration you're using. And here's an interesting tool. When I look at the different families that are available, I'm actually looking at the location of these standard components. So here are the return pins. The system calls retainers. We call them return pins. And their location. Perhaps down the road in my design, I've laid out my water, and it's just one, but it's too close to a return pin. Do I need to move the water? I could, or I could, in this case, move that return pin into some non-standard location. You note down here on the button, which takes you right back to these panels so that you can make changes after you've built up the tool. With that done, let's hit the Finish button, and now we're going to build up all these different mold components and assign them into the different sub-assemblies. So as we go through this, you'll see the A side, B side flashing as it's loading those components. And again, this is a nice feature about working in assembly and controlling the assembly this way, because when I get into doing, I can just simply turn off the A half and look into a nice B plan view. All of these are parametric solid components too, so that you can edit them very easily and do whatever type of to them. So in just a few more seconds, we'll have this mold design completed in terms of the overall layout, the plate, and the component locations. Okay, now for the sake of visualization, I'm going to go through the assembly structure. Some nice thing here is the ability to turn on and off and display the different components, as well as display them differently, display them as wireframe or shaded or transparent. Also change the color in assembly using this tab. Pick whatever color is the appropriate one for you. We'll leave it with the color that's been given to it. Now what I'm going to do is turn off our mold plates. We're going to create a pocket next. And we'll turn off the slide and ejector assembly. So now we're just looking at the inserts with the surrounding components. Next on the wizard is the pocket tool. Here we'll pick the back of the inserts. And that defines the pocket. Now, I guess it helps if I'm in the pocket tool. Okay. Okay. With that, you can assign your fit condition with this offset value. Do you want a slip fit or press fit? Also, the corner condition. Is this going to be a wire EDM pocket with a sharp corner? Is it going to be a mill pocket with a radius in the corner? You can assign all those values. Let it calculate. Basically, it's just going to into both the A side and B side retainer plates. So now we've got our pocket described here. Going into the A side, let's flip this around, and you can see the pocket. Alright, so that's a nice piece of function hole in. Now we need to screw down the A and B inserts, so we'll go into our catalog. Inside our catalogs, we've got components for, you name it, depending upon the type of catalog we're in. I'm a DME inch, so you see all the different components reflected in that. The screw components are listed here. So let's grab a cap screw, and looking through the catalog, we can pick a size. So to start, let's pick one that's 5/16 by 2. And then we're going to place it on the back of the top clamp plate. Rotate this around to the top view. Hopefully that doesn't take too long for display on your system. And we'll turn a grid on to 1/2 inch, which is going to help us to set the locations of our screws. Move this out of the way. Right now on the top half, let's place that. So I'm just going to pick some locations as the grid helps me to find them. You can move it around nice and easily. Notice it jumps everything to a standard grid size. Okay. So there are the 4 screws in their location. Zoom up on one, and now we can go back to edit it. Perhaps that's not the right size. Maybe I want one that's shorter. We can simply hit apply and go through and see what is the appropriate size. What we're adding to the catalog too are rules to help define these things. Maybe you want to set that screw in diameter 1/2 of thread engagement. it'll place it by that value, or if it can't, it'll drive it deeper into the counterbore, or then the option of being the next longer screw. Build those screws in, and watch what happens. You'll see how it builds a hole around the screw. It puts the drill and counterbore into the top clamp plate, and then threads and taps into the insert. What you do to one component or one insert cavity location, you can do to the rest. We'll go back up here to this assembly copy. Pick these screws. Make sure I'm on the screw here. Made a bad pick. Trying to minimize my motions here, that it's going to cause your screen to jump around a lot. So I'm going to copy that from location 1 to location 2. You can see them shadowed in. And to zoom up on that, I want you to watch what happens on this screw. When we build it, not only does the screw go over, but again, knowledge of the hole. Alright, so the assembly copy is working with operator as well as with components. That's an important feature. Okay, now let's jump over into water lines. We'll lay out a quick little water jack here. Let's see, first of all, I'm going to define a plane. So let me exit out of my sketch.